Prototyping is inherently physical and digital, with designers required to work across both domains to reach their desired outcomes. Prototypes that designers use in each domain vary greatly, with a wide range of physical and virtual models that replicate and test product behavior. Each type of model will have its own benefits, and it typically falls to the designer to maximize these while also balancing cost and fabrication time. These strengths are largely bounded by the domain of the model. For example, digital is fast, reconfigurable and flexible, while physical is tangible and accessible, but often at a higher cost. Interestingly, these benefits often fall counterpoint to one another. Where one domain excels, the other often has weakness. Taking a workflow perspective, we typically see iteration between the physical and digital as design progresses. This iterative process introduces several challenges, including the time and cost of transition between domains and the challenges of maintaining learning across many disparate models. Given that prototypes for a single product can number in the hundreds, we can infer just how high these costs may be. This cross-domain workflow raises the research questions of this paper and our wider work. How can prototyping workflow be structured to maximize benefit and minimize cost? And can physical and digital prototyping be better integrated to simultaneously leverage the benefits of each? Recently, there has been a huge amount of relevant work in this space through the paradigm of digital twinning. Digital twinning aims to create a real-life digital replicant of a physical system to as high a fidelity as viable, which is then used to perform multi-physics simulations of system behavior. Outputs are used to understand and optimize the physical system, creating learning action loops that improve system performance. This paradigm has already realized benefits across the engineering sector, particularly in production and operational lifecycle phases of high-value machines. However, research has been sparse in earlier lifecycle phases, including in prototyping activities. Looking again at the workflow over time, we can see why this may be. In theory, a digital twinning workflow comprises persistent virtual and physical entities with real-time data transfer between each to allow their parameters to be synchronized. For this workflow to be viable, both digital and physical entities must then exist, be persistent, and be fair reflections of each other, such that parameters may be meaningfully updated. This is not always the case during prototyping. While many models are present, they are not persistent over time, meaning comparable counterparts don't always exist. Rather than create complete digital replicas of physical prototypes, digital twinning for prototyping raises the question of how prototypes across domains may be integrated to streamline processes and support learning. By creating integrated physical-digital prototypes, the learning action loops that are so critical in prototyping may leverage both physical and digital models simultaneously, reducing the quantities of distinct models that we require and allowing designers to leverage the benefits of each at the same time. The recently maturing domain of immersive reality is the key to this capability. These technologies aim to seamlessly link the digital domain with the real world, such that the digital may be interacted with physically, and the physical may be augmented with digital information. The real-time data connections that these technologies create enable rapid learning action loops that cross the domains. In this work, we want to more broadly understand the potential for cross-domain workflow in prototyping. Looking across 4 cases, we investigate implementation and value of the use of immersive realities to support design. To allow us to understand and compare cases, we first formed a framing to describe integration. In addition to considering the integration of physical and digital models, this framing includes the interaction of the designer with the integrated prototypes. Prototyping is a bidirectional learning and iteration process, and as these technologies have different levels of interactivity, it is important to consider both their transmission of information to the designer and also the way in which the designer then passes information back. Using these dimensions of integration, we characterized 4 cases of integrated prototyping workflow and compared them to current practice, in which all models are typically separate with little to no integration. The second case was Protobooth, a physical prototype digitization platform developed at NTNU. Here the level of integration is fairly low, but the system does allow some intersection between physical and digital through automated information capture from physical models. The third case was CityBlocks, a Lego-based physical city building platform that creates a full-scale virtual reality replica for users to explore. This system kept boundaries between physical and digital, but begins to leverage the benefits of synchronized domains to increase learning while using accessible media as the main interface. The fourth case is a digital mirror, where an editable physical prototype is mapped in real time to a high-fidelity replica rendered on screen. Users interact with the prototype by manipulating the low-fidelity version. This creates visual integration across domains and rapidly increases detail of understanding. The final case is a games controller that requires synchronization across both domains to function. Users freely create their own interface for the controller using buttons that they fix to a physical prototype. Both position and interaction with these buttons are tracked in real time, meaning that users may also physically use the controller to play a simple game and judge its performance. This case shows increased benefits of further integration, where users can seamlessly experience near final product behavior right in the middle of the ideation process. All cases show benefits over current practice, focused around accelerated learning and higher levels of interactivity. Considering interaction between the user and the integrated prototypes, the cases strongly show the benefits of using the digital to simulate behavior and transfer analytic information, while the physical acts as a tangible interface. Considering integration between the physical and digital, the cases show technical feasibility, both of synchronizing models and of updating each based on the state of the other. Higher levels of integration are the enablers for the quicker learning loops that we observe in all cases. However, the technical challenges of doing so are high and must be balanced against the benefits that may be gained. While its methods are not directly applicable to prototyping, the principles of integrated workflow underpinning digital twinning may be realized through immersive realities to accelerate learning and leverage the strengths of each domain simultaneously. This work also highlights several areas for future work. To date, we have little knowledge of best practice, specific forms of value, or how it may be maximized. How we leverage new capabilities is also a challenge in this rapidly developing space. This is compounded by the technical difficulty of implementation. Each of our cases was bespoke and non-trivial, and research should look at how approaches can be rapidly and simply deployed without a large technical overhead. This work has shown the feasibility and value that integrated prototypes may create, but equally underlines that we are early on the path to establishing how we could best use such approaches to maximize value for design. Many thanks for listening to my presentation today, and I look forward to answering any questions.